about weak acids, and we mentioned that they are dominated by the equilibrium constant Ka. And weak acids are very, very common. And how do we recognize a weak acid? Well, usually there will be some subtle language in the problem like X is a weak acid, or an unknown acid with the Ka of the following. If they give you a Ka, it's a weak acid, just by definition. Strong acids don't have a Ka. Their Ka is actually infinite in aqueous solution, so we don't have to worry about them as much. Once we have that little bit of information, well, what if we're not told that it's a weak acid explicitly? How are we supposed to know that it's a weak acid or weak base? Weak acids, and we'll talk about what determines whether something's a weak acid or a weak base, or how strong a weak acid or weak base is in a later discussion. For now, it's easier just to remember what the strong acids are. The strong acids are the common acids we've all heard about. They're usually derived from anions that are stable, things like chloride, the conjugate acid of which would be HCl, or things like sulfates, common ions. Those can be converted into strong acids. Anything that creates a stable anion will create a strong acid. Weak bases are dominated by something called Kb, all of their chemistry, and in many ways it's analogous to Ka, but it's not exactly the same. We haven't done any Kb problems just because we'll be moving on into that area in a second. But these compounds, which ones are weak bases? Again, like the weak acids, it's much easier to remember the strong bases. Strong bases are usually pretty much anything with a hydroxide ion. Those are the only strong bases we're going to typically encounter, or we'll be told it's a strong base. Almost everything else is a weak base. Typically, these are amine salts. They usually have a nitrogen of some sort in them. The prototypical one is ammonia, NH3. That one will pick. That's one of our archetypical weak bases. But there's another type of weak base that we often don't think about as a weak base. So we all know acetic acid. This is acetic acid. Another way of writing it would be HOAC for acetic acid. Now, despite having the OH present, this is not a base. This is a weak acid. Acetic acid, which we typically think of as vinegar, it has a Ka of about equal to 1.8 times 10 to the minus fifth. How do I know that? Because I've done this problem a million times. That's how. You'll be given a Ka, or you'll be given tables. You won't be asked to memorize them. Now, if we have that value of Ka, we can then use that to predict molarities at equilibrium and other values. We've done problems like that. But if we think about this, what about the salt? You take this weak acid and you treat it with a base. What will happen? Well, this is just a neutralization. When we neutralize our acid with the base, we take our HOAC plus NaOH produces our conjugate base. Again, this material consists of H plus OAC minus. When it dissociates, it reacts with the hydroxide ion, leaving us with some sodium chloride. Again, these are net ionic equations, leaving us with the salt. And water. If this is done in a stoichiometric quantity, the amount of H plus and the amount of hydroxide are exactly enough to cancel out, and you're left with just, in solution, this material. Now, where it gets tricky is recognizing that this is a conjugate base of a weak acid. So this is our weak acid, and this is its conjugate base. And another way of looking at this is if we just were to approach this like a typical equilibrium. Again, oftentimes this is the reaction before the reaction. This one takes place. This one takes place. This is general chemistry 1. All of this is converted into all of that. So this reaction takes place. What's left over at the end? At the end, all we have is this conjugate base. That's all that's left. And some water. Now, let's go back a step and take a look at what happens when we drop an acid into water. This is our standard weak acid equilibrium. Releases the conjugate base plus H3O plus. So at the end of, now going back down to this lower reaction, at the end of this reaction, what's left in the solution? Nothing but that, the conjugate base. It is a base. And if we think of this in terms of Le Chatelier's principle, what we've done is we've effectively stacked the deck so that there's nothing but OAC. There's no weak acid, there's no hydronium ion, only the weak acid, or the weak base, excuse me, only the weak base. What that means is this reaction will drive itself backwards, sucking up H3O plus. This H3O plus will go down, creating water and creating acid. If this is a neutral water solution, that means that the conjugate base of this weak acid, when you drop it down into water, will behave like a base. And what that means is, because it behaves like a base, it will suck up protons and create a basic solution. Another way of thinking about this is when we take this weak base, which is called OAC minus, and you react it with water, it will drive itself, it will suck up protons from the water to create hydroxide ion and regenerate the conjugate acid. So here's our weak base reacting with water to produce the weak acid. This is our conjugate base, and here's our weak acid. It always takes place as conjugate acid, conjugate base pairs. So this is why we spent so much time drilling what's a conjugate acid, conjugate base pair, being able to predict. So what that means is that any weak acid, the conjugate base will be a weak base. And vice versa. For any weak base, the conjugate acid will be a weak acid. Now, for strong acids, what this means is that the conjugate base will be extremely weak. What do I mean by this? Well, if you take HCl and you place it into water, H plus plus Cl minus, this chloride so greatly does not want to accept that proton that this reaction essentially lies completely in one direction. And in a similar fashion, strong bases, the conjugate acids, will be extremely weak. So indirectly tied in this weak acid, weak base is the following relationship. It turns out that the Ka of a weak acid times the Kb of its conjugate base will equal Kw. So for a given conjugate acid base pair, Ka for a weak acid times the Kb for the conjugate base of that weak acid, we can use Kw to calculate that value. So in our previous example, we said the Ka of acetic acid, HOAC, was 1.8 times 10 to the negative fifth. We now know that 1 times 10 to the minus 14th divided by Ka, 1.8 times 10 to the negative fifth, will equal the Kb of the acetate ion. Of course, that could be sodium acetate, that could be potassium acetate, that could be magnesium acetate. All of these contain the acetate ion. So we could find that Kb of this material is equal to 5.5 times 10 to the minus 10th. So Ka, just like pH is related to POH, the conjugate acid-base relationship in water are tied by Kw.